Okay, so for 10.6, alternating series test and absolute convergence. So for this section where we're going to look at how alternating series look like, how do they behave, and then we are going to look at the estimation theorem. So this is another test, well, another series for which it's possible to find the infinite sum. However, it's not going to give us the actual sum in the same way that the telescoping series and the geometric series does, because in this case we're going to use an approximation and an estimation to I don't know, to a degree, to a certain degree, to like our or like a certain tolerance to an estimate to plus or minus the 1,000 or 4 decimals, 5 decimals. Well, it depends on how we're going to do this, right? But let's have a look at how alternating series look like. Well, so for alternating series, typically, well, what make them alternating is this -1 to some power, all right? And that could be -1 to the, well, n minus 1, -1 to the n, -1 to the n plus 1, also -1 to the 2n plus 1. I mean, there's many ways to represent this alternating series by these alternating factors, and what they do typically for the, well, for the, at least for the simplest case, they go positive, negative, positive, negative. So that's what an alternating series is. Or negative, positive, well, depending on how the series is defined. Well, the criteria for convergence, it needs to satisfy these two conditions. Number one, the limit of the expression without the alternating factor has to be 0, and we need to show that the next term is less than the previous term. In other words, what we need to show is we need to show that the given sequence is decreasing essentially. That's what we need to show. All right, so let's see. So sequence is non-increasing. All right, that's what it means. It's non-increasing. So let's determine whether each series converge or diverge. All right, so sigma n equals 1 to infinity of -1 to the n power times 1 over n. All right, so number one, we need to check two conditions. Letter A, or number one, limit of the expression b sub n approaches infinity, which is limit in this case, n approaches infinity of simply 1 over n. Again, it's without that alternating factor, only the remaining part of the expression. Where is this limit going to? 0. First condition is satisfied. Second condition, is b sub n plus 1 less than or equal b sub n? Well, let's see. What we're going to do here is b sub n, which is simply 1 over n. And this b sub n plus 1 in the subscript means that we need to change every single n in our sequence with n plus 1. That's going to turn this into a 1 over n plus 1. All right? Is that inequality true? Yes. All right? The denominator on the left-hand side of the inequality is a larger number, making the actual value, the overall value, a smaller quantity, checking with the inequality, of course. All right, so let's see. In this case, the series converges by the alternating series test, AST. All right. Let's have have a look at the next example, letter B on the next page. So for B equals, so what do we have? Sigma n equals 1 to infinity of negative 1 to the n times n squared divided by n squared plus 5. So number one, condition number one, limit b sub n approaches infinity, that is limit n squared over n squared plus 5. And what is this limit actually? 1. Well, in this case, this is not a 0. Alright? And this means diverges. Does that look familiar to something we have done before? If so, what is that? Isn't it really like the n-term test for divergence, the very first test we did, in which the limit has to be of any number different than 0 in order to diverge? So it was a test only to determine divergence, right? So in this case, well, the first condition failed. No need to do the second one, so we're done. Let's have a look at letter C. Oh, sigma n equals 2 to infinity of cosine n pi over the square root of n. Well, in this case, this series at first glance doesn't look like alternating. It doesn't have a negative 1 to the n, or a negative 1 to the n plus 1, or negative 1 to the n minus 1. However, this cosine n pi is what will make this series alternate. Okay, let me list some terms of the sequence only for the cosine part, for the cosine portion. Okay, for n equals to, well, we start at 2, 3, equals to 4, and equals to 5. Cosine of 2 pi, cosine of 3 pi, cosine of 4 pi, and cosine 5 pi, etc. What's cosine of 2 pi? 1. What's cosine of 3 pi? Negative 1. What's cosine of 4 pi? Cosine of 5 pi? Did you see the alternating? Okay, we can rewrite this series in the following form. N equals to 2 to infinity. That's a negative 1 to the n, 1 over the square root of n. And let's see if this works. So for n equals to 2, we get negative 1 squared. Yes, that's going to make it a positive. All right? That's fine. That's correct. So now we may look at the two conditions. Hopefully they're satisfied. All right. So, yeah. So let's see. Letter number 1, letter I rather, limit b sub n approaches infinity has to be 0. Let's see if it is. Limit n approaches infinity of 1 over the square root of n. Well, 1 over the square root of n at infinity, 0. First condition is satisfied. For the second condition, is the sequence non-increasing, or in other words, decreasing? I mean, either one or the other. Well, that is b sub n plus 1. Is that less than or equal b sub n? Well, 1 over the square root of n for b sub n, and for the term on the left hand side of the inequality, we need to shift this n with an n plus 1. Now, is that inequality true? Score. This means, because both conditions are satisfied, this means that the series converges by the alternating series test. All right. Okay. Questions about alternating series for what we have so far? Alright, so what's next? Well, so when it comes to alternating series, we need to further discuss the convergence of the series. So that is, we need to determine whether an alternating series further converges absolutely or just converges conditionally. Well, so what we're going to do is we're going to take the absolute value of the given series. Well, when we take the absolute value, those alternating factors just go away. Then we're going to come up with a whole new series for which we will determine its convergence or divergence using the tools that we have so far up to this point. If the new series happens to converge, then the original or alternating series converges absolutely well because it converges for the absolute value of the series, However, if the new series happens to diverge, well, then that original series convergence were only conditionally. So, well, here is on the next page we have this diagram that we need to follow. So number one, so we're given a series, an alternating series right here. All right. So we need to make sure that these two conditions are satisfied. Number one, the limit for b sub n without the alternating factor equals to 0, and that the sequence is non-increasing. Then if both conditions are satisfied, well, then we go this way. All right, we go to the convergence. Whoops. It converges now, and this is what we did so far. Just check the conditions. From here we will take the absolute value of the series, and number one, if the absolute value of the series, which is a whole new series that converges, then converges absolutely, but otherwise converges just conditionally. If, like in one of the examples that we did before, at least one of these two conditions fails to be met, diverges, we're done. All right. So let's have a look at one example to determine whether the series converges or diverges, but absolutely this time. Okay, so number one. And by the way, for this kind of problems, we are going to use like more than one test in one whole problem, though. But of course, overall, the alternating series test. That is, number one, limit b sub n approaches infinity equals to 0. In other words, whether the limit of 1 over n squared plus 8, notice I'm not writing the alternating factor, we don't do it for this part of the series, and where is that limit going to? 0. So the first condition is satisfied, we're good. Second condition, non-increasing. That is, okay, on the right hand side, the original, and on the left hand side, shift the n by n plus 1. What about that inequality? Is that inequality true? Yeah. Yes, because n between n squared on the right hand side, in the denominator on the right hand side, and n plus 1 squared on the denominator of the left hand side, well, that n plus 1 getting squared is going to make that denominator larger, giving us an overall left hand side to be a smaller number, satisfying the inequality, which is good. Both conditions are satisfied. Now let's create a whole new problem. And for the whole new problem, that means sigma n equals 1 to infinity of negative 1 to the n plus 1 of n squared plus 8. We need to take the absolute value of this series. And what this absolute value does is to eliminate any alternating factors. So the new series will be sigma n equals 1 to infinity of 1 over n squared plus 8. Alright? For now, forget about the alternating series. Let's focus on this new series that actually doesn't happen to alternate. Well, let's think about it. Which test would we use to check for convergence or divergence for this series? Well, p-series will be involved somehow, but I mean, just p-series is not just enough because of the plus 8, right? If it only said 1 over n squared, well, p-series convergence and the original series just converges, absolutely, we're good. However, that plus 8, a comparison test, and in this case, use the comparison test that best works for you, or the one that is shorted. In this case, I'm going to use the direct comparison because the limit comparison is going to make me write a bit more. So, but of course you can use the limit comparison test. In fact, both of them work. And so compare with sigma n equals 1 to infinity 1 over n squared. What do we know about this series, by the way? 1 over n squared. It's a convergent, what kind of series again? P-series. Alright, convergent. So in this case, we will do the tiny less than or equal to small. Alright, less than or equal to small. And so the tiny, which is the original problem, 1 over n squared plus 8, is that less than or equal to 1 over n squared? Yes. Okay, so here we're going to backtrack a bunch of information. So number one, this absolute value of the original problem will do whatever the test series does because we were able to show that tiny is less than small. So in other words, this series will converge by direct comparison, okay, with 1 over n squared. So, and now going back or backtracking to the original alternating series, because the absolute value of the series was convergent, then the original problem converges absolutely. All right, converges absolutely. Let's look at another one. Letter B. Well, number one, the first condition, limit n approaches infinity of n plus 3 over n squared plus 2n plus 1. What is that limit equal to? 0, right? It's polynomial over polynomial. The degree in the denominator is larger than that in the numerator. We're good. 0. First condition is satisfied. The next one would look a little bit tricky, but don't worry. You'll see. So, okay, on the right hand side, let me write the original sequence, n over n plus 3 over n squared plus 2n plus 1. And in the left hand side of the inequality, replace every single n with n plus 1. That's going to make the numerator an n plus 4. In the denominator, we're going to get this n plus 1 squared plus, okay, this 2n will become 2n plus 2. Do we agree? But that plus 2 plus 1, well, let me just leave it. Let me make it, I mean, don't need to expand the whole thing. N plus 4, n plus 1 squared plus 2, n plus 1, it's fine. No need to simplify. Yes, this inequality looks a little bit complicated, I agree. And especially that's going to make us hesitate a bit because of the left-hand side potentially being bigger than the right-hand side, because here we have a 4 and here we have a 3. Do we agree with this? However, adding one integer to the numerator is not going to do much harm to the value of the series. What will really do harm is adding one integer to the quantity that gets squared in the denominator, right? That's going to make the denominator being larger and overall giving us a smaller value, which in this case we'll check with the inequality. That's enough. So on the exam, you're given something like this. You don't need to write me a paragraph. Oh, okay, no. Just say yes. That's fine. Okay. Sometimes you could be asked to like solve the inequality. That's gonna take forever. Don't. Here we trust each other. I mean, yes, it is. We know you know that I know. You know, that's fine. Okay. I mean, I think it's clear. Despite the number of symbols and powers, I think it's clear. Okay. Sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1, n plus 3, n squared plus 2n plus 1. Okay, get rid of the absolute value bars by getting rid of the alternating factor n plus 3, n squared plus 2n plus 1, and we need to come up with a simpler series. So again, it looks like we will have to use some kind of comparison, isn't it? Okay, let's see if there's anything we can compare it with. All right, so compare with. Okay, so in this case, for the comparison for the test series, I'm going to neglect the lower degree terms on both the numerator and denominator. So I'm going to write just n over n squared, all right? And well, n over n squared is the same as saying 1 over n. What do we know about 1 over n? Divergent, what kind of series? P series. And from here, do your preferred test, direct comparison or limit comparison. I'm going to do the shorter one. I'm going to do the direct comparison. Well, for divergence, in this case, we're going to do huge greater than or equal to big. That is huge, which is the test 1 over n. Is that greater than or equal the original problem? I mean, again, we could be a bit hesitant about this n plus 3 on the right hand side of the inequality, making this eventually larger. But again, it is the denominator, what gets bigger, faster, and we only have this, right? So this is true. And what does that mean? We need to be careful when backtracking the information here, backtracking the conclusion. Converges conditionally. I mean, we got diverge, all that, everything worked. However, we go with whatever we obtained from the new series. So the absolute value of the series diverges. For that reason, the original alternating series will converge conditionally. All right.